everybody to my new lecture. Our subject today is fossil fuels. So fossil fuels, are coal, oil and gas, and I told you in one of my previous lectures that about 80% and more of the primary energy we are using is fossil fuels. Today we learn where fossil fuels come from, why it's so important. In a later lecture we will focus on some new concepts here. So as you know already, since 200,000 years humans have been using renewable energies, and only 170 years ago we started to burn fossil fuels at a large scale. And before we go into the current times today, I would like to tell you something about the time scales of our whole world, because you have to get a feeling on how things appear and disappear again in the history of our world. And the other point is fossil fuels come from a time very long ago, and you should get some feeling about what these time scales are. So let's start with the timeline of the world. The nice things about being a scientist is you can get a feeling on how things have been a very long time ago and how they are today and how they developed. So science nowadays has a big knowledge of all those things. As a physicist, we know that there was a Big Bang, and after the Big Bang, the universe, how we know it today, has been created. This was 13.8 billion years ago. As a physicist, you call a billion giga. So 13.8 giga years ago, the Big Bang happened, and then the universe expanded and became the way it was today. If you ask me as a physicist what has been before the Big Bang, before the universe has been created this way, well, we don't know. Of course, it could be that there was something before. It can also be that there are many more universes in our world, not only the one we are living in, but this goes far beyond the scope of this lecture. The next important thing for us was the creation of the Earth. The Earth was created about 5 billion years ago. So this was 9 giga years later. At that time, the atmosphere of the Earth was mainly CO2, CO and hydrogen. So it was an atmosphere where any life we know it today would immediately die. At this beginning, Earth was very different from what it is today. Then, and this is about 3.8 giga years ago, life appeared on Earth. So the life at this time were single cells, very primitive forms of life. And this was only 0.8 giga years after the Earth was created, only 800 million years later. And if you think about the evolution of biology, some people say the creation of the first cells after 0.8 giga years was, the time was too short to happen on Earth. Other people again say nobody knows where life comes from. Apart now from religious ideas, the scientific ideas are that of course life could also come from outer space somewhere. What is the argument here? Well, we know the time when life came to our Earth, this was 10 billion years after the universe was created, and only 800 million years after the Earth was created. So if life would have been created in outer space somewhere, there was really much more time. Almost 20 times the time between the creation of the universe and the creation of the Earth compared to the time when life was appearing on the Earth. Why do people think life could be created somewhere else in the universe and then came to our Earth? Why? Because we know that there are some types of life which could easily be moved as for example, as a meteorite from another galaxy or from another part of the universe to us. We know that even more complex forms of life can survive in outer space, even freely, not only inside of, for example, a frozen meteorite. These are the tardigrades, as you see it here on the picture. Tardigrades, or how they at the beginning were called little water bears, they are micro animals, and from those we know they can even survive as individuals in outer space. People have found them at the outer side of spaceships. And in this sense, of course, single cells and spores and bacteria in principle can also survive, at least inside of a frozen block of material which is transported through the outer space and falls down on our Earth. But this is not our subject. The main point is 3.8 billion years ago, life appeared on our Earth. But at that time, the atmosphere was still free of oxygen. Oxygen appeared only 2.4 gigayears before our times. This is again about a billion years later. There were cells now that could do photosynthesis, and that is the time when plants started to convert CO2 into oxygen. And at that time, the oxidant contents of our atmosphere increased. Then it was the age of plants growing everywhere, and about 300 million years ago, so again a very long time afterwards, that is where the Earth age, the geological age of the Carboniferous appeared. Carboniferous means there's carbon in the Earth, in these geological structures. What does it mean? It means that is where most of our coal appeared on Earth. What is coal? Well, we all know that most of our body contains of carbon, oxygen and hydrogen. In other words, carbon and water, or carbohydrates. And just as our body, also the body of all other animals and plants consists of these elements. So if you have these carbohydrates and you take out the water, you're basically left over with carbon. That is why the remains of plants and trees are basically only carbon, so coal, if you take away the water, and which means the oxygen and the hydrogen. So that is the time where our coal comes from. This lasted, however, only for something like 60 million years. What happened 300 million years ago? Well, that was the end of the time where this coal was produced at large scale. This was caused, the end was caused by climate change. It has to do with the movements of geological regions on the Earth. It produced a climate change, and at the same time, at this time, a new kind of fungi was created by life, and this fungi was able to decompose lignin. Lignin is a part of the plants which all the other life on Earth could not decompose. So the bacteria and the fungi before this time were not able to digest lignin, and therefore if a tree died, it fell on the ground and did not decompose, and then it was covered by other plants and by dust and soil, and that is why all these remnants of plants appear now as coal underground. 300 million years ago, then these new fungi decompose plants. Therefore, normally when a tree falls down in a forest, it's basically completely eaten up by fungi and bacteria and other animals. And then nothing is left from this tree. Therefore, today we do not have fossil remnants in the ground anymore at a large scale as it was 300 million years ago. Let's continue the time scale. 335 million years ago, the dinosaurs appeared. You all know them from films nowadays. Then 200 million years ago, the mammals appeared. And the dinosaurs, they lived for a very long period on our Earth, more than 150 million years. This was a very successful kind of species, and they survived a lot of changes of climate and everything. But then 66 million years ago, dinosaurs were extinct. We believe nowadays that a meteorite hit the Earth and that the climate changed, and due to the change of climate, dinosaurs, like they were at these times, were not able to survive. There was not enough food, it was too cold. And then dinosaurs disappeared, the big dinosaurs, but we know nowadays that what was remaining of the dinosaurs were dinosaurs which had feathers and could fly. And these dinosaurs, we call them nowadays birds. So birds are the remnants of dinosaurs. So in this sense, dinosaurs were not extinct completely, but they continued to live as birds nowadays as we know them, all until today. Then it took a long time, so we were talking about millions of years now. Now we talk of thousands of years. About 200,000 years ago, the Homo sapiens appeared on our Earth. And the Homo sapiens was very clever. He had a bigger, a more sophisticated brain in some sense compared to cats and dogs and whatever kind of animals were around. And he was using fire to burn wood and other stuff. So he was starting to use renewable energies. As I told you last time, he also used solar energy, wind, geothermics and so on. And that is how we as human beings lived for 200,000 years. Then we go another 3 orders of magnitudes further, so from thousands years, from 200,000 years, now we come to years. It's only about 170 years ago that humans started to use fossil fuels at large scale. That was the beginning of the industrialization. We invented machines which were driven by fossil fuels, and with these machines we were able to dig in a more efficient way for additional fossil fuels, like we do it today. We have coal, later when we had oil, and finally gas, natural gas. Today we are at the beginning of the Anthropocene. As I told you in one of my previous lectures, the Anthropocene is the time where human beings have so much impact on the globe that they change the large-scale behavior of our globe, as well in terms of weather and climate, as also in pollution. The humans started a new extinction of species at large scale, and this is also the time where we have to switch to renewable energies. This is zero, this is today on a global scale, and as a physicist we also know how the Earth will continue in the far future. We know that the energy at our Earth, all the renewable energy, mostly comes directly from the sun. And this sun is a nuclear fusion reactor, and this nuclear fusion reactor will be out of fuel in the far future. It takes about 5 gigayears, so 5 billion years, until the fuel, the hydrogen in the sun is burned. Then there will be a new process happening on the sun, and this new process will expand the sun to a very large, big red giant ball. This is called then the change of the sun as we know it today to a red giant, and this red giant will blow up the Earth completely, so there will be no Earth left. There's no chance for us to survive on the Earth. In this sense, the Earth was produced or was created about 5 billion years ago. It will be destroyed in about 5 billion years. So we are just in the middle of it. So we could say that the Earth today is in a midlife crisis because it's just 5 billion years old. It's just half of it, of the total lifetime of the Earth. And in 5 billion years, it will be destroyed. So the Earth has lived half of its life, and it's now to us, if we stop our civilization today, or if human life continues for many more thousands and maybe millions of years on this planet. Now we got an impression about the time scales of our Earth, how it changed. And I have to show you one more plot in this context now, because that will be very important for our lecture on climate change and greenhouse gases. So the plot here shows you the concentration of CO2 over the last 400,000 years. So why is it so important and what is happening here? Well, I told you at the beginning of the lecture that at the beginning of our Earth, CO2 had a very large content, was one of the main parts in our atmosphere. And that is an atmosphere where people like us, or also all the animals, cannot live. So how did it change in the meantime? Well, so life, which consisted of single cells and bacteria and all kind of very little forms of life, at some point was able to do photosynthesis, as I told you before. Photosynthesis uses the energy of the sun to change CO2 and to produce oxygen out of CO2. What is the advantage of a plant doing so? Well, the advantage, of course, is that a plant consists mainly out of carbon, oxygen and hydrogen. Well, the oxygen and the hydrogen comes from the water. Life started in the water. But where to get the carbon? The easiest way to get it from is to get it from the atmosphere. So if you are able to change CO2 into solid forms of carbon, then you have your own building blocks produced for the plant from the atmosphere. So the carbon is what the plant needs. It uses the solar energy to produce carbon from CO2, and the remaining gas is then oxygen, which is the output, the byproduct of photosynthesis. And then at some time animals appeared. Also the plants use oxygen, but the animals finally need it for life. What do animals do? Well, animals typically eat plants. They eat, in this sense, molecules which consist of carbon, oxygen and hydrogen. What do the cells of the animals do? They produce from the carbon and the oxygen, they produce CO2 again, and they gain back the energy which the plants put into these molecules. This you all know from biology classes. So in a way, this is the first example of what we call today the circular economy. So the plants use CO2 from the atmosphere and water from the seas. They produce their building blocks from it, and then the animals take the carbohydrates, add oxygen, and produce energy from it and CO2. So in this sense, in biology, carbon is the energy carrier for the animals, but at the same time it's a building block as well for plants and animals. The same is true in our modern technology, but we will come back to that later. So if we look at this plot here, which shows the CO2 concentration over the hundreds of thousands of years, you see the concentration is very little. So what happens in the last million years? Photosynthesis was happening in excess, and this way the CO2 concentration was further and further reduced, and instead oxygen was given away by the plants to the atmosphere. That is why today we have a high concentration of oxygen, about 18%, and the concentration of CO2 is almost zero. We are nowadays at about 300 ppm, which means 300 parts per million, so it's much less than 1%. So basically zero CO2. In addition to photosynthesis, at the beginning there were also geological processes playing a role for that, but for our purpose here the photosynthesis is the main point here. And we see since effectively about 650,000 years the CO2 concentration is constant, and that is because there is an equilibrium of the photosynthesis and the decomposition of plants and animals. This equilibrium is contained because whenever there is more CO2 in the air, there's more photosynthesis going on, and the photosynthesis produces carbon from the CO2, takes it out of the atmosphere, and then at some point the plant degenerates and decomposes, and the animals as well, and then the CO2 comes back to the atmosphere. And this equilibrium is working since about 650,000 years now in a very stable fashion. The fluctuations which you see come from ice ages, so from climate change, and only today, since about 1950, there's a steep rise of CO2, and this steep rise comes from the burning of fossil fuels in an extended way, how we do it in our industrialized world today. So details about the climate system we will discuss in the future lectures. Today I would like to add one more thing here. The reduction of CO2 at the same time means an increase of oxygen, and our body needs oxygen to live, and actually we are at a very low concentration of CO2 in our world, and human beings only exist since 200,000 years. And if the concentration would be higher, if for example the CO2 concentration would go up to 8%, we would be dead immediately. 8% leads to an unconsciousness less and a death within less than 1 hour for human beings. And for CO, it's even much smaller. So in this sense, for human beings, CO2 is a lethal gas. Yeah, it's a very dangerous gas. Large concentrations of oxygen and together with low concentrations of CO2 and carbon monoxide in the ambient air are a prerequisite for the genesis of animals. Why is that the case? Well, All animals use the combustion of organic materials to produce energy. In biology, you call it the cell respiration, as I explained before. This only works if the CO2 concentration is at a very low level. The human brain is one of these pieces in biology which uses very much of oxygen. So it's not the muscles only which use a lot of energy. Our human brain is even worse in this respect. It really needs a lot of oxygen and a very well functioning lung to be able to function properly. And therefore, for man, a low concentration of CO2 and a high concentration of oxygen is very important. So this is already the end of this clip here. The next clip will talk also about fossil fuels, but this time we will focus on a certain aspect, which is peak oil and fracking, certain modern ways to use fossil fuels. So today, thank you again for listening and see you next time.